The one of the important concepts in the heat topics, that is the kinetic theory of the gases, and that we'll be discussing here. So we can expect a regular question from this particular chapter, that is kinetic theory of the gases. So regarding it may be the specific heat conditions, or it is the RMS, that is the relations between the specific heats. Okay, now the relationship between the RMS velocities or the different types of the velocities. Specific heats in the sense you can be going CP, CV relations and the relation between them and the RMS velocities and the different types of the velocities, please. Next one, relation between the, that is the kinetic energy and the temperatures. So these are the very important things in this particular category. Okay. So now coming to this particular first part of this one, we'll be going for a specific heat, please. So what do you mean by the specific heat? It is an actually the amount of, or the, it is the required heat where to rise the temperature of any particular gas per 1 degree centigrade. For 1 mole of a gas, for 1 degree centigrade, I want to rise that particular thing, please. Okay, so this phenomenon, whatever you are going to call it as a, is called as your specific heat conditions. Okay, so there will be two types of the specific heats over here. One is an CP, and which is called as an molar specific heat at constant pressure, and CV is called as an, it's an same thing, molar specific heat but at constant volume. Because on rising the temperature, uh, there will be both pressure changes as well as the volume will also change. So when you want to study about the one thing, that is when you want to study about the pressure, so we'll be keeping the volume constant, and we want, when you are studying about the volume, you want to keep the pressure as a constant. So by the definition of this one, the anything or the CP or the CP can be written as n, that is 1 by n into it is dq by dt, and the same thing CV can be written as an, it is 1 by n into the same relationship, but in one case you will be placing the pressure constant, and another case you will be placing the volume constant. So now from this one, the total heat that can be written as an, it is n Cp dt for the pressure constant heat supply. Whereas in the case of the volume constant, this can be written as an dq, or the heat supplied, is equal to n Cv dt, and this one will be numerically equal to your internal energy of the system, where which depends on the temperature. Okay, so now when it's going to be depending on the temperature conditions, so you'll have the three types of the internal energies, or du is composed of the three types of the energies basically. So one is an, it's kinetic energy, internal kinetic energy, and it is an rotational energies. Another one is an vibrational energies. So three types of the energies if you have. So based upon the degrees of the freedom, now coming to the degrees of the freedom conditions, the same internal energy according to the equipartition energy, that is geo energy, can be written as a F by 2 into number of moles into RT, where F is called as your degree of freedom. So what is this degree of the freedom? This is nothing but it is the number of ways in which a molecule can store the energy. For example, a monoatomic molecule is there, it can store the energy along the x-axis, y-axis and z-axis, that is the three translational energies will be there. Or for monoatomic, the degrees of freedom is going to be the three along the x comma, y comma, or z axis. Three types of the kinetic energy, three translational energies it will have. Whereas the diatomic energy, the total energy will be according to the equipartition energy. The total energy will be stored or the 5 degrees of freedom. Out of that one, 3 translational plus 2 rotational degrees of freedom. So that means 3 in the along the x-axis, y-axis, and z-axis. 3 translational kinetic energies it will have. Another one, 2 rotational kinetic energies, that is half I omega square, and another one is also the half I omega square. So whereas for the polyatomic structure, it will consist of an uh, polyatomic gas. In this case, the degrees of freedom we can take it as a 7. So that is 3 translational only, 2 rotational, and 2 vibrational degrees of freedom. So as we are discussing about the specific heat of the body, so the specific heat of the body, or the ratio of the specific heat, or the relation between them, Cp minus Cv, is equal to R, and the ratio of the specific heats, that is Cp by Cv, is equal to gamma, where gamma can be called as the ratio of the specific heats, and the relation between the gamma and the degrees of freedom can be written as an 1 plus 2 by F. So all these relations are very, very important relationships. And the Cp can be written in terms of the gamma. It is gamma R by gamma minus 1. Whereas the Cv can be written as an in terms of the gamma terms R by gamma minus 1. Okay. So these are the representations of the Cp and Cv. And your Cp value and the Cv value for the monoatomic and the diatomic. First, I'll go for the Cv and the diatomic gases and the polyatomic gases are. So, monoatomic gas, the Cv is going to be it is 3R by 2 degrees of freedom. Here you can see 3R by 2, it will be and this one is going to be the 5R by 2. That is the Cp value. So, now in this case, for the diatomic, it will be the 5R by 2, and this is 7R by 2. The ratio of them will give you your gamma value, or for the polyatomic gas, it can be multiple this thing triatomic, or you can say that one it will be the 3R, and this one is going to be the 4R. So these are the different values, but don't consider that your specific heat value or the CV value remains constant. So please don't take it into the consideration that CV is a constant values, please. So these specific heats are not with the constants. For example, if I take the helium, which is a monoatomic gas, under the temperature of some 700 Kelvin, it's going to be the monoatomic, and its CV value remains as an 3R by 2. But when its temperature crosses some 1000 Kelvin here, then its vibrational modes will be converted, or the degrees of freedom will be converted from 3 to 5, then it will be the 5R by 2. And when it crosses some 1500 Kelvin, so the degrees of freedom will be the 7R by 2. Okay, so depend upon the temperature thing, the CV values will changes, and so the corresponding your CP values will also change. So please be careful of that particular thing, please. And the CV value you can also write in terms of the degrees of freedom as. So CV can be written as an in the sense here I'll write the is CV can be written as an okay. So sorry. Okay. So CV can be written as an in terms of the degrees of freedom if I want to write it. So CV can be written as an it is F by 2R, since it is 3R by 2, 5R by 2, and 3R. So on that sense, CP can also be written as an CV plus R. From this relationship, CP minus CV is equal to R. Or you can write it as an F by 2R plus R. So depend upon the question, whatever is been asked to you, Try to express the CV and CP in those terms, please. Now, coming to here, there is an example given that is 4 grams of gas occupies 2.4, 22.4 liters of the at NTP. The specific heat capacity of the gas at constant volume. What does it mean? Specific heat capacity at constant volume, in the sense it should be your CV value. He has given it as a 0.5. Let us note it down. CV is equal to 0.5 joule per mole Kelvin. Okay, so now if the speed of the sound in the gas at NTP is going to be the velocity of the sound, he has given it to be the 952 meter per second. So he is asking that the heat capacity at the constant pressure is going to be how much? That is, he is asking the CP is going to be how much? So this is the specific heat of the gas at constant volume. Now this is the given thing is mass. This is your volume. These are the conditions at NTP and all these things. Okay. Now what does why can't we use directly here CP minus CV is equal to R? Because here you are finding the CPC. So where the CV is nothing but an internal energy conditions. There might be some work done because of that one, some heat it might be extracting or some extra energy might be added. So due to that, all these things. So we'll be trying to go for the velocity relation, please. According to the RMS velocity for relationship, you can write the VRMS is equal to. So it can be written as an root over gamma RT. Sorry, velocity of the sound can be written as an. He's talking about the sound gamma RT by molecular weight, or general formula of the sound is going to be the gamma into pressure by density rho. So this is converted into the RT by M here. So now as he has given this value and temperature at the NTP we need basically. Temperature at the NTP will be the 273 Kelvin. This is the known values. And coming to the molecular weight conditions here. So the mass he has given, volume is there. Okay, so R value he has provided it as an 8.3. Fine, sir. So now substitute everything. This is going to be the mass condition. So I'll write for squaring on either sides. Then gamma can be written as an this is m into v square by m into v square by RT condition. So substitute every value here. 4 grams in the sense 4 into 10 to the power of minus 3 velocity square. So that one. So velocity square in the sense that will be the 952 whole square by this will be the 8.3 into 273. So this is the one we need to solve. So I think so on solving this one, it is 10 power 3, denominator is more. Almost this is tending towards the 1000. So 10 power 6 might be here, and here it is 10 power minus 3. Then you will be left over with the 10 power 3000 by 8.3 into 273. I'm going for an approximation, sir, here. So I don't, since we don't have the time here, going for an approximate values. So this will be almost around the 4 times, and 16 by this will be around 1.6 or 1.7 you should be getting. So as you know the gamma value, and Cp by Cv is equal to gamma. From this one we can determine Cp is equal to gamma into Cv, where the gamma is going to be the 1.6 into your CV value, sir. So what's your CV value is going to be here? Substitute that CV value here. 0.5 joule per Kelvin or whatever it may be, or most probably it should be the 5. So because options are more than that particular thing, so this might be the 5 in this case. So it should be the 8 joule per mole Kelvin. Okay. So if it's 0 is not, then it will be the no problem. 8 joule per mole Kelvin. Right. So now So our next concept is going to be what is this is an RMS velocity. What is this RMS velocity conditions is an it's a root mean square velocity where it's an approximation of the velocity of all the molecules which are in a container. So VRMS is equal to root over 3RT by molecular weight, or this can be written as a 3KT. K is called as a Boltzmann constant. Okay, so according to this Boltzmann constant, and this is the R value where capital M is called as a molecular weight, and it is the temperature dependent function. Basically, VRMS is equal to. Okay, so and another one is going to be your this is an universal gas constant. So VRMS is going to be the is directly proportional to the square root of temperature conditions, please. It is directly proportional to the absolute temperature. That means as temperature increases, your RMS velocity will also increase here. So this is the one of the important things, sir. You need to remember this one. And if you try to find out the ratio of this RMS velocity to the speed, those type of the questions can also be asked here. That is VRMS, that is RMS velocity by velocity of the sound, which can be written as a root over this is 3RT by molecular weight, and this one is equal to root over gamma RT by M. This is your velocity of the sound case, please. So, sir, now in this case, for dividing the ratio, so velocity VRMS by velocity of the sound can be written as an as these values are going to be changed. It is 3 by gamma. So depend upon the gamma value or the type of the gas that is being used over there, you can substitute this particular gamma value and you can solve this particular solve these things for the corresponding cases. And you can also there are the different types of the questions will also be asked on this one, whereas one will be the RMS value, that is the average values. Another one is a most probable velocity. So what is this most probable velocity condition is? Most probable velocity, suppose if there are in a container like this, if there are 10 molecules are there. Okay, 10 molecules are there, for example, or n molecules are there. They will be moving in a random direction. They will be moving in their different orientations, directions will be there. So the velocities of it is an average of. Generally, if you go for the most probable velocities, out of the 10 molecules, if there are 5 molecules which are having a velocity of 10 meter per second, and 2 molecules are having some 11 meter per second, and another 3 molecules are having some 7 meter per second like this, then according to the most probable velocity conditions, you need to choose the that value of the velocity where you will have or the number of molecules mostly having them. So most probable velocity is that velocity where the lot of molecules are possessing it. So in this case it will be the example that is 10 meter per second. Okay, na? So in this case it will be the 10 meter per second. This is your most probable velocities conditions, and most probable velocity will be equal to the some 0.6 times of the RMS velocities, please. 0.6 times of your RMS, sorry. So 0.6 times of the VRMS conditions. And whereas average velocity is nothing but a sum of all the velocities by number of velocities, which will be V average can be written as a 0.8 times of the VRMS velocities. Okay, so these are the very important things regarding the RMS velocities. So please be careful of this one. So RMS velocities can also be written in another format as VRMS can also be written as a root over 3p by rho. Also, you can use it depend upon the situation over there. Fine. So now, when we look at the questions on this particular thing, the molecule of a given mass of the gas having the RMS velocity. So there is a molecule over there. So of a given mass of a gas is there, which have some RMS velocity like this. So he has given the RMS velocity at a given temperature as we have just studied. VRMS velocity is directly proportional to square root of absolute temperature. He has given the V1 RMS velocity is at T1 temperature as it is 200 meter per second at a temperature of the 300 Kelvin. He has given in terms of degrees centigrade 273 plus, excuse me, this is 27. So now this is the relationship, please. Now, and at this temperature and the pressure also he has given. Now, when the temperature and pressure of the gas are being respectively 127 and this one, he is asking about the RMS velocity of the molecule. So, as we are discussing about the temperature and moreover the pressure has it doesn't have any impact over here because in the RMS velocity relationships, just now we have written 3p by rho. When pressure changes correspondingly, your density will also change. So the ratio of the p by rho doesn't have any impact on the RMS velocities here. Individually, they show them. So we'll be better going for the temperature. So V2 he is asking at a temperature T2 is equal to 127 in the sense it should be the 400 Kelvin. So now put it in the relationship over there that is V1 by V2 is equal to root over T1 by T2. If I substitute there V1 by V2 is equal to V1 is equal to 200 meter per second by V2 is equal to root over. This will be the 300 by 400. Just go for the calculation part of this one. That is V2 velocity 2 is equal to 200 into 2 by root 3. Okay, or else if you want this one as a 200 by root 3 by 2, you can go for this as a 200 by 0.866. Root 3 by 2 value is 0.866, or else in this condition he has leftover is as an this is 400 by root 3. So this should be your answer. Okay, so these root 3 by 2s, 1 by root 2 values, root 3 values. So these values has to be remembered, please. So now coming to the relation between your kinetic energy and the temperatures. So how does this kinetic energy and the temperature are being related? So according to the equipartition energy theorem, whatever the energy is there, that energy, internal energy, total internal energy, is can be written as an F by 2 into uh, n number of moles into R, that is universal gas constant into temperature. So in the sense, your internal energy, whatever may be the case, that internal energy depends upon the degrees of freedom. So for example, if I go for the monoatomic gas, for the monoatomic gas, the total energy U will be distributed into the three types of the kinetic energies, that is equal to the half, uh, that is your Boltzmann constant into temperature along the x-axis plus half kT into y-axis plus half kT along the z-axis. So distribution, it's going to storing the energies along the x-axis, y-axis and the z-axis. So three different modes of storing of this one or summation. It will be the 3 by 2 into kT, or this is I'm writing it as a 3 by 2 into nRT, where this 3 represents in comparison of these two things. 3 represents your F, which is called as a degrees of freedom. Okay, so now as temperature increases, your internal energy will be increased. Since that, so in that condition, your kinetic energy or whatever it may be, that is going to be directly proportional to the temperature in this case. So when temperature increases, your internal energy increases, in the sense your internal kinetic energy increases, because the total internal energy is distributed into three parts, which is your translational kinetic energy, KE translational, and KE rotational, and KE vibrational. So it will be three types of the energies as temperature is being increased. So when temperature increases, it will be stored in the three different types of the kinetic energies: translational, rotational, and vibrational. Translation will only have the three storage modes, X, Y, and Z axis. That means the molecule can move along the X axis, Y axis, and as well as your Z axis. In this molecule, it can move in this direction freely, in this direction freely. So the free movements of this molecule, monoatomic molecule, where it can to have the energy stored, is nothing but three ways. That is the translation kinetic energy. So coming to the rotational kinetic energies, as I've already mentioned the translation, rotational kinetic energy is moment of inertia along this omega square and half I y omega square, like this. So rotational kinetic energies it will have, and the vibrational kinetic energies also for the triatomic or the polyatomic gases. Okay, so this is how the as the temperature increases, internal energy will be changed. When you take out the temperature from the gas, the internal kinetic energy will be decreased, or if temperature is going to be increased, then internal energy will also increase. If temperature is going to be decreased, then internal energy will be decreased. If temperature remains constant, then U will also be constant, and the change in internal energy will become zero. So please remember these parameters, man. Now, coming to this one, increase in temperature of a gas filled in a container would lead to. So, as we have discussed, what will happen when temperature is going to be increased? What will happen when temperature increases? Increase in internal kinetic energy, or kinetic energy will be increased. Fine. So, now coming to the different questions that we need to solve. Okay, this is your first question. A cylinder contains a hydrogen gas at a pressure of 249 kilopascals and a temperature of 27 degrees centigrade. So he has given the pressure is equal to 249 kilopascals, 10 to the power of 3 pascals. Great. And the temperature small t he has given that in degrees centigrade. So in the absolute scale, it will be the 300 Kelvin. R also he has given, since it's an hydrogen H2, then generally on the parameters it can be written as an 2 grams over here. Mass is going to be the 2, or that is 2 into 10 to the power of minus 3 kgs. Now its density is going to be how much? So how to write the relation, please? According to the ideal gas, PV is equal to nRT. So gram weight by gram molecular weight, I'm going for this one, please. Now P into volume can be written as a mass by density is equal to mass by gram molecular weight into R into T. From this one, density can be written as an, that is a pressure into molecular weight by R into temperature. This is your situation. So now here we need to write the pressure, which is 249 into 10 to the power of 3 pascals, into molecular weight, that is gram molecular weight is 2 into 10 to the power of minus 3 by R value he has given in the question itself, 8.3 into 300 temperature. So obviously this can be removed here. So this will be the, you can solve it in the proper way, please. That is 18, 9, and this one is 498, approximately 500, and you can go for the solving case, please. And if it is going to be 500, this is 8.3 into this is 300. So 500 by 3 something else. I'm going for an approximation, which is 5 by 3 into 8.3, which is 24.9, or this is going to be the 25. Okay, so if I write this one as a 25, this will be the 1 by 5. 1 by 5 in the sense 0.2. Yeah, I've gone for an approximation, so this can be your nearby value, please. So as he has asked about the density, so units will be obviously kg per meter cube. Okay, so now next question here. Two vessels separately contain two ideal gases. One is A, another one is B. Okay, there's same temperature. Okay, there are the two vessels. Let's name them as A. Another vessel, let me name them as an B. So both of them are ideal gases. Separately, the temperatures are the same. So this is T, this is T. The pressure of being twice that of the B. That means the pressure of the A is equal to 2 times the pressure of the B. So this is the information he has given. First one, fine. Next one, under such conditions, density of the A is found to be the density of the A is equal to 1.5 times the density of the B. Great. Next one, the ratio of the molecular weights he is asking. Pressure he has given, density he has given, temperature is same. Then he is asking the molecular weight. So which how to solve this one? We have just derived P by rho is equal to which is equal to the R T by molecular weight. Anyway, R is constant. He is asking about the molecular weight. Let me take the molecular weight to one side. Then it is rho density into temperature by pressure. So on that basis, molecular weight of the A by molecular weight of the B can be written as an density of the A by density of the B. Since temperature is same, I need not to write that one. So that is inversely proportional to the pressure in the sense PB by P. Now substitute the values. Rho A by rho B is 1.5. PB by PA is 1 by 2 from these two things that we have written separately. So 1.5 by 2 comes out to be the 0.75. So what is the 0.75 value is 3 by 2. This is your information. Next one, at what temperature will the RMS speed of the oxygen molecule become just sufficient for escaping from the Earth's atmosphere? At what temperature will the RMS speed of oxygen, okay, becomes just sufficient so that it has to escape from the Earth's atmosphere? So what is the escape velocity of the Earth is going to be 11.2 kilometer per second. This is the value we know. That means your velocity of the oxygen should come out to be 11.2 kilometer per second. Or else if I try to convert this one, this is 11.2 into 10 to the power of 3 meter per second, or it will be the 11,200 meter per second. So your RMS velocity has to be this much. So this is the given information. VRMS he has given. Boltzmann constant also he has given. Mass of the oxygen molecule he has also small m. And what is the leftover thing he is asking what's the temperature is how much. So VRMS is equal to root over 3 into Boltzmann constant into temperature by small m. So what is this small m value is going to be? He has given everything. So from this one, just write the temperature T is equal to how much, sir? T is equal to that will be the VRMS square into m by 3 into K into Boltzmann constant into temperature. Sorry, temperature this one. So temperature T is equal to VRMS. That is 11200 whole square into small m value is 2.76 into 10 to the power of minus 26 by that is your Boltzmann constant 1.38 into 10 to the power of minus 23. Now solve it, please. And 3 is also there here. So it's one hell of a question or calculation, heavy calculations thing. Okay, so this is the how you need to solve this one. Now coming to the next case where the gas mixture consists of the 2 moles of oxygen is there and 4 moles of number of moles, N1 is equal to 2 moles, N2 is equal to 4 moles. One is an diatomic, this is the oxygen is diatomic, and argon is going to be the monoatomic. So at the temperature T, neglecting all vibrational modes, that means the total energy is distributed only in the translational kinetic energy and the rotational kinetic energy terms. Please. Then he is asking what is the total internal energy. So total internal energy should be equal to the energy of or your total energy of whom? Of the oxygen plus total energy of the another one which is your argon. So these are the two energies we need to identify out. So how to find out this one? What are the degrees of freedom for the O2? For the O2, degrees of freedom are going to be the 5 because it's a diatomic and argon is a monoatomic. It will be only 3. So based upon the degrees of freedom, this is 5 and this is 3. Can we find out their individual internal energies? That is, U is equal to F by 2 into number of moles into RT. If it is 1 for an oxygen, so this will be the O2. Then F by 2 into number of moles. Number of moles of the oxygen are going to be the 2, and the degrees of freedom for the oxygen will be the N1 value is going to be the 5, and into 2 into RT, R value and the T value. So this goes, which is the 5 RT. Okay, so this is the internal energy of the O2, and now the internal energy of the argon AR can be written as an same thing, but the degrees of freedom will be the 3. 3 by 2 into RT, which is 3 RT. Then the total internal energy U is equal to U2O2 plus UAR is equal to how much, sir? Which is okay, this is 3R. Had I mistake written? Okay, this is 4 moles now. Sorry, 4 moles in the sense this goes for 2 times. This is going to be the 6. So total is going to be the 5RT plus 6RT. Then final answer is going to be the 11RT. This is your relationship. Option C. So next one, man. A 15-gram mass of nitrogen gas is enclosed in a vessel at a temperature of 27 degrees. So nitrogen N2 diatomic, and this is your M. Temperature is there, which is going to be the capital T is equal to 300 Kelvin. The amount of heat transferred to the gas so that RMS velocity is going to be double. So he wants the RMS velocity to be double, that is VRMS is equal to root over. So double this one, that is 3 pressure by density. Or this can be written as an root over 3 RT by rho. Okay, so 3 RT by M, molecular weight here. From this one, VRMS is proportional to the square root of temperature. In the sense, your next temperature, whatever is going to be the transfer, that is T2 is equal to 4 times of T1. Since velocity is being doubling, that is V1 by 2, V1 is equal to T1 by T2 whole square. From this one, T2 is equal to 4 times of T1. This is the one we have got from here. Now, as we know that heat produced is equal to NCV dt, change in internal energy is equal to delta T. From this one, NCV into change in temperature is T2 minus T1, which is equal to the NCV of T2 minus T1. This is the one. T2 is 4T1 minus T1. This is going to be the 3T1. Substitute all the values close to this one. N value is going to be how much, sir? Gram weight by gram molecular weight, 15 by 28 here. 15 by 28 is n value, and the CV value is 5R by 2, and this is going to be the 3 into temperature is 300. So this comes out to be R value also you need to substitute, ma'am, and solve it. Most probably this should be coming out to the 10 kilojoules. Okay, so these are the type of the questions that can be asked. Very, very important thing. Apart from this one, in the kinetic theory of the gases, please go through the mean free path for formulas and the relation between the pressure and the kinetic energies, that is 3 by 2 kT, and all these things, please. So these are the very, very important chapter for the even for the final examination. Okay, so your next class or whatever it may, next class is going to be your maths class. So please join to the Mr. Neil sir at 7:30. So this